Hi everyone, welcome to another episode of This Week in Space Science right here at Columbus State University, and with me, Dr. Sean Cruz, Executive Director of the Coca-Cola Space Science Center. Sean, how are you?
I'm good, Mike. How are you? Good to be here.
Well, I'm glad you're here today too. We just have a lot of fun when we come in and do Twiss. We get to, one of the things we might need to do is roll cameras before the show and just talk and let the audience know what we're talking about and the conversations that we have sometimes, because all of this is very interesting to me, and I'm glad you're here. Today we're going to talk about some things going on out beyond Earth. Beyond our solar system.
Indeed.
And even our galaxy, if you will, and
well
out there. So that's fun. All right, so we're going to talk about something very interesting, and if you don't know about it, never heard of it, this is a great time to learn about it, and it's called gravitational lensing.
That's right, that's right. We've got a really neat discovery that we're going to talk about here at the end of the show. One of the most distant galaxies ever observed has been observed, but the way that it was done is partly due to this phenomenon in nature that we call gravitational lensing. And gravitational lensing, it's both bizarre but very fun at the same time to talk about and to think about. And so you're right, that is what we're going to chat about here on the show today.
You know, one of the things that I'm aware of too is that we're looking at some of those Hubble telescope pictures, and you brought in many of those that show that deep field shot of all of the galaxies. The further out you go, and we've got some wonderful pictures of those galaxies, entire galaxies that look like little tiny dots out there until you get closer to them. And so the idea of going further and further out and just seeing all of the wonderful components of our universe and making sense of those. Well, we've got to talk about it, because one of the things we do when we point a telescope at these things is that it's not always just a straightforward shot of that. There are a lot of things that could interfere with our view.
That's exactly right. Interfering is exactly what gravitational lensing is all about. So first of all, let's talk about lensing, and then we'll figure out how gravity can do this weird process of lensing. So I brought a couple of props with me here. I've got a couple of pieces of glass in my hand.
All right,
and the first piece of glass I have in my hand is just round. It's just a round piece of glass. It's flat. The light passes straight through this piece of glass and just travels on its way. It was slowed down for a very brief time as it passed through the glass, but it was done so in a uniform way. And so as it passes out the other side, it just keeps going in a straight line, which is why I can look through this piece of glass and nothing looks distorted. And that's why we make windows and things that we need to see through out of flat, parallel plane pieces of glass. Now, if I was to take that same piece of glass and cause the edges of it to be curved, then light would travel through that at different velocities depending on where along that piece of glass it traveled. That's what happens with this. This is a lens. And if I show you the lens sideways, it's fatter in the middle, skinnier on the edges. Now, if I turn that around, you might see a very distorted view. In fact, you can probably see me in there upside down.
Yes,
there's a shot of me in there upside down. And as you can see, I'm back here behind the lens, but you can see me through the lens as if I was right there with the lens, and my face is distorted. It's smaller, it's upside down, there's some weird stuff going on. That's all because of the light travel paths through this piece of glass being distorted by the fact that light is slowed down at different amounts depending on where the light hits this lens. So lenses can be made in a particular shape. They can be tasked for particular purposes. So we have the shape of lenses in certain shapes and sizes to accomplish different goals. For one of those goals is to correct vision right on your face. And so these glasses that I have, these lenses on my face, they're bent in a specific way to facilitate the problems with my eyes, to allow me to be able to see as if my eyes were perfect and I wasn't looking through glass at all. And so we can also use lenses with telescopes, and they can help us bring distant objects into view and magnify them and gather more light and concentrate that. So those are all the uses of normal lenses. But now out there in the universe, Mike, there's this weird thing called gravitational
See, I've got to
lensing.
wonder, gravity comes in and distorts this light in some way.
It does.
Like you're talking about the shape of those lenses.
It works like a lens, but there's no lens there. It's just the gravitational field of very massive objects. And the reason that light can do this, it can be bent around massive objects, has to do with some principles that we find in general relativity. That was one of the theories that Einstein first gave the world, this concept that mass tells space how to behave. Or in other words, mass tells space how to be shaped. Now you might think, well, you're talking crazy talk. You know, space is empty. How can it be shaped like anything?
I don't know. We've heard on this show before, space is not empty, it turns out.
Space is more complicated than it would first appear. And this is some of the principles that we've gathered from Einstein's theory of general relativity. There is this thing called the space-time continuum, or when we're talking about the specifics of relativity, we call it the space-time manifold. And light travels along the space-time manifold just like a ball rolling along a flat surface. And so that's the way light is traveling through normal space without any mass in it. But what happens is, when a mass is present, the phenomenon that we call gravity is actually that mass bending and warping and changing the shape of this underlying four-dimensional space-time manifold. So then when light comes along and it's traveling through the space-time manifold and it hits this area where mass is contorting that manifold, it rolls just like a marble would roll along that curved space. So light is rolling around a bent shape if it is traveling in the area of a massive object through space. Now, that phenomenon is what we know as gravitational lensing. And I think we have a shot here that we'll show you of the Hubble Space Telescope. This is a cartoon, but it's the Hubble Space Telescope looking past some objects here in space and seeing some things in the distance. And actually, I was referring to a second shot, but this is a great shot right here. This is a simulation of what the mass of a supermassive black hole in the Milky Way would do to the light behind it. So this is not a real photograph.
Okay.
It's a real photograph of the Milky Way behind, but it's a simulation of how a massive black hole, a supermassive black hole, in the foreground would bend the light from those stars in the background and how we would see it. So if we were somewhere near the area of space, near the supermassive black hole at the center of the Milky Way, it might look a little bit something like this. So all of the light that you're seeing there is being bent around that black hole, which you see in the center of the frame right there. But that black hole is bending the space-time manifold around the outside of that pretty strongly.
Yes. And
so this is a warp that works very similar to the lens that I just showed you on camera a moment ago.
And the larger the object, the more this lensing takes place, because that's very, very distorted as we're looking at that picture.
You're exactly correct. So this is a distortion simulation of about a 1 million solar mass black hole. In other words, a black hole with 1 million times the mass of our own sun. But even that mass, which is very, very large, is small in comparison to a galaxy, an entire galaxy. The Milky Way galaxy has 4 billion stars in it. So some lensing can happen with even bigger objects like galaxy clusters. In other words, not even just one Milky Way galaxy, but a whole bunch of galaxies that are clustered together in a group. And when you get those kinds of galaxy fields all together in one big ball, and you have objects that are further off in the distance, the light from those further objects passes through that area where you have this giant ball of galaxies, and it's really warped and bent. And now I think that's leading to the cartoon I meant to show you a minute ago, with Hubble Space Telescope viewing some distant galaxies, that the light from those distant galaxies are actually traveling by that big ball of galaxies right there in the middle. So as we're looking at the photograph, Hubble, the cartoon, remember this is a photograph of a cartoon, right? This is a simulation. Okay. Hubble Space Telescope is on the right-hand side. Some simulated fictitious distant galaxies are those little blue ones on the left-hand side. You can see the light from the top and bottom galaxies. They travel straight to the Hubble with no problem. But that galaxy in the middle, the light wants to travel in a straight line right through that big ball of galaxies in the center, that orange ball. That's that galaxy cluster. But it can't do that because that space is warped. So what happens is light from that distant galaxy that's trying to travel around the edges of that galaxy cluster is bent back to Hubble Space Telescope. Now what does it see? Well, it sees what appears to be the top and bottom of those two galaxies. Mm-hmm. That's where the light looks like it's coming from Hubble. So what Hubble sees instead is a little blue galaxy above the galaxy cluster and a little blue galaxy below the galaxy cluster, when really all of that light is coming from the same object, the galaxy that we see in the middle on the left-hand side right there. Does that kind of thing really happen in the universe? Do we really see these bizarre formations in the universe? And the answer is yes. And the photograph I brought in to show you here is what's called the Einstein cross. And so this is the Einstein cross right here.
Okay, tell us about this. This is very interesting.
This is very interesting. It's actually a distant quasar, which is a distant galaxy core, very, very far away, that the light from that distant quasar is passing by a galaxy cluster in the middle. And what happens is that galaxy cluster in the middle lenses the light from that distant quasar, and what you see are 4 quasars around the central bulge of that middle galaxy right there. You see 4 images of the quasar, but those aren't different quasars. That's the same object.
Okay.
So the lights on the top, bottom, left, and right-hand sides are all the same object, but the light from that object is being lensed by that foreground massive object, because that foreground massive object, its gravity is warping the space-time manifold, and light's traveling in weird ways around it. And so you see 4 images of one distant quasar.
So that's really a measure if you're looking at one of these things and see 4 in that particular pattern. Does that Einstein cross, does that happen often? Because there's a lot of objects out in space.
There are. And the answer to that's yes. I mean, there's a lot of objects out there that are powerful enough to bend space so that distant objects, the light from them is warped. And so we do see several examples of that. However, that Einstein cross I just showed you, that's one of the most pure examples of just a really neat looking lensing pattern that can be explained relatively simply. And here's the interesting part. When astronomers first saw that, they did not know what they were looking at, because they started they thought those were 4 separate objects around there.
Obviously.
They started looking at the spectra. In other words, they let the light go through a prism or a spectrograph, and they started looking at the emission lines and absorption lines in that spectrum. They realized it all had the same fingerprint. In other words, it was the same object. Top, bottom, side and side, all the same object. How could that possibly be? Well, the only way it can be is if there's some massive foreground object causing light to bend around it in weird ways, and you're seeing 4 images from one object created by the massive object in the middle. That's what gravitational lensing is.
So it's actually that pull from that center object. The gravity must be tremendous for that to take place, or they have to be very close, or both, perhaps.
Exactly, yeah, and you're right about that. But yes, you're looking at the mass of something that's tremendously massive in the middle, which has a very large effect in warping that space-time continuum and allowing that light to be bent in weird ways. And so that's going to kind of lead us to where we need to talk about today, some very interesting things going on. Because see, it turns out that gravitational lensing can be used as an actual tool. So just like we use lenses to build a telescope itself, we can actually use the lensing that happens in these galaxy clusters, these big groups of galaxies, to act like a second lens for us, to help magnify even more than our telescope can magnify and see even further objects. And the next image we have here is just a great example of a foreground cluster. Here you're seeing it all in the little yellow colors here. That's the foreground galaxy cluster lensing galaxies that are much, much further away. And they are the blue ones in this particular photograph. So particularly on the left-hand side, if you can look, you will see little arcs of blue light that almost make sort of a circular shape. If you kind of connect the dots all together there, those are the warped images of far distant galaxies that are being lensed by a galaxy cluster, and the cluster's name is Abell 2218. So this cluster, this foreground galaxy cluster, lensing the light from those more distant galaxies, it's actually the warping of that space-time acting like a lens that even allows us to see those blue galaxies. They would be too faint and too far away without the lensing effects of that foreground galaxy cluster acting like a secondary magnifier to allow us to be able to see this. And of course,
yes, excuse me, but it's all those galaxies in there together that are really forming even a larger gravitational pull and allowing you to get around that and see those streaks of those galaxies.
Exactly right. It's the effect of all the combined gravity from all those galaxies which happen to be hanging out together in this cluster that really warps that region of space very dramatically, turning it into a lens that allows us to see those much more distant galaxies behind in a way that we wouldn't without that foreground lens. So that's how we can actually, if we can find this lensing phenomenon, we sometimes get a little bit better look at the objects that are behind because there is this foreground warping going on.
Amazing.
So that's pretty neat. Now, I mentioned in that conversation of the last galaxy cluster right there, I called it an Abell cluster.
All right.
And that word is Abell. That's the last name of a very famous astronomer by the name of George Abell. And George Abell, here he is right here, exactly. He was an astronomer at UCLA. And I'd like to tell a story about George Abell before we talk about all of his contributions. The great thing about George Abell is he started out as an amateur astronomer. He started out at a public astronomy facility giving tours to the general public of the nighttime sky and the observatory. That was at the Griffith Observatory in Los Angeles. So that's the way George Abell got his start. And you know, we here at the Space Science Center at Columbia State University, that's what we do. We allow for people to come in and view the nighttime sky or view the simulated sky in our planetarium. And we have a whole bunch of students here at Columbia State University who are participating in educating the public about space science and astronomy, just like George Abell did. And we're hoping that those students then go on to be great contributors to the field of astronomy and astrophysics.
Well, he's proof that it can happen, absolutely.
Exactly, that's exactly right. So George Abell at UCLA was participating in something called the Palomar Sky Survey. Now, Mount Palomar, a giant telescope, the Hale telescope in California, came online in the early 1900s. Astronomers were doing serious work with that telescope. In fact, it was the largest telescope in the world for many years. During the 1950s and 1960s, there was a whole lot of very serious work being done there, cutting-edge research from the Palomar telescope. And one of the things they did is they just photographed as much of the sky as they possibly could with this brand new, massive, 5-foot in diameter telescope. Remember, a lens, except they used a mirror on the Palomar telescope, but it's 5 feet across, much bigger than this. So that really gave these astronomers a brand new view of the universe at the time. So as they photographed the sky, they collected all that together. They called that the Palomar Sky Survey. Well, then they had to have astronomers go through all those images and say, what do we have here? We photographed the whole sky. We've done it with more light gathering power and more magnification than we've ever had before. What are we finding? George Abell, one of his jobs and one of the things that he decided to look for in the images from the Palomar Sky Survey were these galaxy clusters themselves. So he put together a list that is now called the Abell clusters. There are over 4,000 of those galaxy clusters that George Abell identified. They had some basic properties. Number one, they were rich in galaxies. So in other words, that grouping had 30 or more, which later became 50 or more galaxies in their groupings. And they had to be fairly far away. They had to be more than a redshift of 0.2, which translates to about 2 billion light years away. They had to have a pretty good distance to them. And so they were distant, rich galaxy clusters that Abell was able to identify in the Palomar Sky Survey. So that's why we call these objects Abell clusters. And the story that we're going to tell you today has to do with an Abell cluster.
All right. We got to hear about it. I've got a tip on this one, but I want to let you introduce this one.
It's a brand new set of imaging coming from Hubble Space Telescope and Spitzer Space Telescope combined, looking at the Abell cluster, the Abell cluster 2744. So Abell number 2744, 2,744 in that catalog of over 4,000 of these clusters. They pointed the Hubble Space Telescope, Spitzer Space Telescope at that same cluster. They gathered imaging from both of those. If you don't know about Spitzer, it's an infrared telescope. So Hubble was observing in the optical, Spitzer in the infrared part of the electromagnetic spectrum. They combined these data together to create a combined set of images to be able to look at. And what they found was that Abell cluster 2744 was doing a powerful job by gravitational lensing of imaging even further, more distant galaxies well beyond the cluster. In fact, some so far away that they were galaxies that are very nearly to the beginning of the universe. Now, the concept I want to get across here is this. When you look further away in outer space, you're also looking further back in time. That's because light has a finite speed. It's 186,000 miles per second. That's how fast it travels. So that's like a mail delivery man, right? So this mail delivery person is way out there in the universe, and it takes some time to bring that letter to you so that you can have the information that's in that letter. Well, light is a finite speed mail delivery person that begins way out there at the edge of the universe, but takes a long time to get here. And so the further away objects are, the longer it takes for light to get here, which means when we look at objects that are further away, we're seeing them the way they looked in the distant past when that letter was first sent, not the way they look today. So when we look at distant objects, we're also looking back in time. We're seeing the early history of our universe. And that's very exciting for astronomers, because when we look in the local neighborhood and we see the Milky Way galaxy and the Andromeda galaxy, we see the way that galaxies look today. But how did they look a long time ago? Well, we can't see how the Milky Way looked a long time ago. All we can do is see how it looks today because we live inside of it. In order to tell what galaxies looked like a long time ago, we have to look at galaxies that are very, very far away.
Right.
And so when we look at those galaxies that are far away, we say, oh, well, this must be kind of a snapshot of what galaxies were doing in general in the very distant past. That is what leads us to today's story.
All right, here we go.
This week in space science. So a group of researchers, I'm going to get the names right. So they're from two institutions, the Instituto de Astrofísica de Canarias, the IAC, I said that badly, but
right.
Instituto de Astrofísica de Canarias. It's the Institute for Astrophysics in the Canary Islands, and La Laguna University. So these two universities, these two groups of researchers, were using both data from Spitzer and Hubble to look at this cluster, Abell number 2477, and look at the distant galaxies that were being lensed by that cluster. And I think we have a photograph from this group right here.
All right.
Let's take a look at this photograph. So this, on the left-hand side right there, you're seeing that very distant cluster. And on the right-hand side, you're seeing one little galaxy that's being circled there. Now, if you look back at that left-hand image, up in the upper left-hand corner, you're going to see a blue box.
Okay.
That little blue rectangle up there is a representation of the photograph that you're seeing on the right-hand side and where it would be sitting in that field. And actually, Daniel, I think if you can go back an image, I think we have one more image that's a close-up of that cluster right there. Let's go back. There we go, right there. There's a shot of the cluster. So that photograph that you were seeing is somewhere in the upper left-hand of this photograph. But as you can see this cluster right there, you see all those big, bright galaxies toward the middle, and then you see all kinds of little tiny lines, little tiny galaxies scattered all through that field. Those are the more distant galaxies that we're being able to see because of the effects of gravitational lensing. And so that little red galaxy we saw in the previous picture is one of these very distant galaxies being lensed or being imaged by the foreground cluster, Abell 2744. So now maybe we can go forward again. We'll see this other photograph. There it is again. There's the cluster on the left, a little blue rectangle. Here's the close-up shot. This is what we now term as Abell 2744, and then it gets the subcategorization of Y1, and that's just their cataloging system for cataloging the individual galaxies that are visible in that photograph. This is Y1. Well, Y1 isn't part of that foreground cluster at all. It's really a very distant galaxy. So the next step is to say, well, how distant is it? If we can go forward, maybe an image now, we'll see a close-up of just that galaxy. If you can imagine, they take that little tiny piece of light, and they run that little tiny piece of light through a spectrograph and get a spectrum from that. And from that combined observation, they're able to tell that this galaxy is indeed extremely distant. They use techniques to determine how far away it is, and they determine that this galaxy is over 13 billion years, light years away from us. So in other words, we're looking back over 13 billion years back into the history of the universe. Well, now here's the interesting part. The universe is only thought to be about 13.8 billion years old, right? So the light that left this galaxy that we see in this photograph left that galaxy when our whole universe was only about 625 million years old. A tiny fraction of the age of the universe today. So this is what a galaxy looked like when the entire universe was in its infancy. This is one of the very oldest objects ever imaged. It's what galaxies look like when the universe just barely had matter forming together in it. So the whole concept of matter had just condensed out of the energy field just a few million years before that. And so this is a primeval, primordial galaxy object that we're seeing. It's about 30 times smaller than the Milky Way. So in size, this was a very small galaxy, even compared to our modern day Milky Way. However, it was forming stars at a rate of about 60 times greater than our Milky Way is today. So it's smaller, but it's just forming stars at an alarming rate, an incredible rate, compared to what the Milky Way does today. So it was a growing galaxy at that time. So, you know, think about a little seedling of a tree, and today the Milky Way is like an oak tree, right? So, so this is a very interesting set of objects out there, and a very interesting set of observations that was done by this. And we're truly looking back at one of the oldest objects ever observed by human telescopes out there in the universe.
That is amazing. I mean, there's always something going on out there, but now we're using gravitational lensing, which I thought originally was a problem for us, but we actually have manipulated that a little bit to look even further than we can with these wonderful telescopes like Hubble and Spitzer.
And truly, gravitational lensing can be a problem. You can see why a distorted image may or may not be a good thing, right? But it's the classic case of turning lemons into lemonade. How can we actually use that weird bending of light from these distant objects as a lens to help us see even better? And so this is one of those great examples in science where thinking people say, no, wait, this is helping us out. We're going to be able to see better or further or more improved observations than we would have otherwise. And so an incredible scientific effort, very interesting subject. The bending of light by gravity.
I'm absolutely thrilled by this notion. It's good to have this kind of information. We don't get it everywhere else. Ladies and gentlemen, you're watching This Week in Space Science. Dr. Sean Cruz and I'm Michael Baltimore. Each week here on Columbus State Television, right here at Columbus State University in Columbus, Georgia. We invite you to watch us each week, anytime, for Twiss. We'll see you next time.
Thanks, Mike.